Alright, so let's say you had a system of equations, right? And let's say that, traditionally you've probably looked at systems of equations with two variables, but you can have a system of equation with an infinite number of variables, right? And so what we're talking about today is this idea of, let's say you had a system of equations that looked something like this, where you had, three variables as such. And so you have x minus y minus 2z is equal to 5. You also had y plus 4z is equal to negative 5. And then you also had z is equal to negative 2. Now what does this do for us, right? We are basically given a system of equations with three equations, three variables, and what is the key thing about this equation, this system right here? Well, the key thing is that we can actually substitute in each of these kind of values and determine each of these values in kind of a systematic way. We're given that z equals negative 2. You can plug that back in over here into the second equation over here to find y, and you can plug in the values of both y and z into the first equation to find x. And so what this form of a system of equation is called, it's called triangular form. I'm going to write that down. I'm going to highlight it as well. It's called triangular form of a system. And what that means is that you have kind of a structure to this system that looks something like this. Whoops, that looks something like this. Kind of like, sort of like a triangle, whereby you could back substitute, per se, could back substitute in each of the specific values of variables that you already know into the previous equation in order to calculate a certain variable, and then back substitute again. This is also known as row-echelon form, and it really is helpful for us when we're trying to solve multivariable linear systems. And an algorithm that we use in order to transform our traditional linear equations, where you could have a number of variables in each of the equations, to kind of this triangular or row-echelon form, we use a method called Gaussian elimination, and the operations used to produce these equivalent systems are called elementary row operations. So let's talk about those elementary row operations. And so this kind of connects back to the idea of a matrix as well. And so you're hopefully familiar with matrices, and so these are operations that you can actually do on matrices, and they translate very easily back to the idea of a system of equations. And so what this does for us is that it allows us to manipulate systems of equations that or previously have different variables and different equations, and what it allows us to do is that it manipulates those equations to put them into row echelon form, making it much more easier to solve. And so those operations, I'm going to write them down here. Those operations there are three main ones. Okay, you can interchange two equations. Equations, two equations. You can also multiply one of the equations by a non-zero number. I'm just going to write multiply by a non-zero number. And then also you can add a multiple of one equation to another equation, and that's the key thing here. Adding two equations. All right, so you can do a number of things. Interchange equations, multiply by a non-zero number, or adding two equations. And we're going to see an example of that, hopefully in the next problem, where you can actually do these things, and then also these also translate to matrices. And that's the key thing here. Systems of equations and matrices go kind of hand in hand in these elementary row operations, and you can apply both to each other in order to get your system into row-echelon form. And so we're going to be using the process of Gaussian elimination in order to accomplish that. So let's take a look at an example. Alright, so this question is asking us to write the following system of equations in triangular form using Gaussian elimination, and then to solve the system. Alright, so first things first, what are we going to do? Well, we can first actually declare each of these equations. This is going to be our first equation, our second, and our third equation. I'm going to draw a line underneath it. Alright, so we first can just rewrite the first equation. We can leave that as is, because that contains all of our variables. Oops, that's not a minus. That's going to be a 6z, 17. Alright, now what can we do with the second and third equation? Well, we can add them together. We can add them together and cancel out that negative 2x and 2x, because negative 2x plus 2x is just going to be 0. So adding them together, we are left with just an equation containing y and z. So what is that going to look like? Well, negative 2x plus 2x is 0. Like I said, negative y plus negative 5y is going to be equal to negative, that's going to be equal to negative 6y. 24z plus 12z, well, that's just going to be 36z. And then 12 plus negative 30, that's just going to be negative 18. Now, what can we do with the first and third equations? Well, we can certainly, for example, multiply the first equation by 2. What does that leave us with? Well, if we multiply the first equation by 2, I'm going to do this in a different color. I'm going to multiply the first equation by 2. So 2 times the first equation is just going to be 3x plus 9y minus 6z is equal to 2 times 17. What does that look like in practice? That's going to look like 6x plus 18y minus 12z is equal to 34. All right, that doesn't look like much now, but watch what happens. I'm going to shorten this so that I have enough space for the third equation. Now, what am I going to do with the third equation? I'm going to multiply that by 3. So I'm going to do that in a different color as well. I'm going to multiply that by 3. So 3 times 2x minus 5y plus 12z is equal to 2 times negative 30. 2 times negative 30. Well, what does that look like in practice? Yet again, that's going to be 6x minus 15y plus 36z is equal to negative 60. So what can we do from here? Well, we can actually subtract 2 times the first equation from 3 times the third equation. And in doing so, we can actually eliminate those two x's yet again. And why are we allowed to do that again? We're allowed to do that because that is that is one of the elementary row operations that we're allowed to do. We can actually add two equations after multiplying them by a non-zero number. So let's do that. Let's add 2 times equation number 1 and 3 times equation number 2. Or sorry, subtract 3 times equation number 3 from 2 times equation number 1. All right, so let's do that. So I'm going to do this back in black. So 6x minus 6x, that's just going to be 0. 18y minus 15y, well, that's going to be 33y. And then negative 12z minus 36z, well, that's going to be negative 48z. And then 34 minus negative 60, that's going to be equal to 94. All right, or actually, sorry, I think I made a slight mistake here. I have multiplied this value by 2 instead of 3. So in order to fix that, I'm just going to change it as follows. So multiplying this by 3 instead, that leaves us with negative 90 over here. And so in doing so, we actually have 30 minus negative 90, so that's going to be 124. So let me change that value to 124. And so that leaves us with, now we have one equation containing x, y, and z, but now we have 2 equations containing y and z only. Okay, so now what can we do with this? Well, we can certainly leave the first equation yet again as is. Minus 6z is equal to 17. Let me actually bring this canvas down a little bit. And so we can leave that as is. We can also kind of, in order to simplify this a little bit more, we can subtract, we can divide this whole equation number 2 by negative 6. And that is the same thing actually as multiplying by negative 1 over 6, which is one of the elementary row operations. And so that will leave us with y minus 6z is equal to 3. All right, we're good there, and we can leave the third equation as is. 48z is equal to 124. All right, now what can we do for our final final act in order to get rid of the y in this last equation over here? Well, we can certainly multiply this equation by 33. And what happens when we do that? Well, let's do that in a dark blue. So we can multiply this equation by 33. I'm just going to go straight to it. We have 33y, 33 times 6 now. 33 times 6, I'm going to do some quick math. 33 times 6 is going to be 198, so minus 198z. And 33 times 3 is going to be 99. Let me erase that now. Over here, we can leave the 33y and minus 48z as is. So I'm just going to leave that as is. And so what do we see immediately? Well, what we see is we can actually subtract both of the equations. And so subtracting both of these, augmented equations, you get 100. We get, and actually let's do that down here over here. So I'm going to leave the first equation as is. I'm going to leave the second equation as is as well. And so what are we left with in our third equation? We're subtracting both of these, the 33y and the minus 33y, that becomes 0. Negative 198 minus negative 48, well, that's just negative 150z. So negative 150z, and that's going to be equivalent to 99 minus 124, which is negative 25. All right, and so this is our equation in triangular form, and we have that there. Now we can actually just solve for z very easily. So z is going to be equal to negative 25 over negative 150, which is 1 over 6. Y is going to be equal to, well, we can substitute in the 1 over 6 to z over there, and so that leaves us with just 6 times 1 over 6, which is going to be 1. So y minus 1 is equal to 3, and so y must be equal to 4. And then the x, we can plug in the 4 and the 1 over 6 into y and z respectively. And so what that leaves us with is 36 minus 1, which is 35. Bringing 35 onto the other side, we have 17 minus 35, which is negative 18. And so negative 18 over 3 is negative 6. And so that is the solution to this system of equation. Now, it's kind of tough to do because this was actually done through equations. We can actually translate this over to matrices, and it's not that hard to do. So why don't we look at another example doing this in matrix form. Alright, this problem is asking us to solve the following system of equations using Gaussian elimination. And so we're given a system of equations, and we're asked to basically find the solution. And so what can we do? Well, recall matrix multiplication, where you could actually do ax is equal to b. A times x, for example, is equal to some matrix b. Well, actually, we can fill this A over here with a coefficient matrix, what we like to call a coefficient matrix, where, for in this example, we have 1, negative 3, 1, and we have 2, negative 8, 8, then you have negative 6, 3, and negative 15. Let me make sure I got that correct. So we have 1, negative 3, 1, 2, negative 8, 8, and negative 6, 3, negative 15. All right, we can multiply that by this second matrix, which is just going to be containing x, y, and z. Because if you'll remember, we're multiplying the rows of matrix A by the column of matrix B, and so if you look at that, that actually works out to be, the dot product essentially of these two vectors, which are the rows and the columns of A and x respectively, and that's going to be equal to a solution matrix, which is going to be 4, negative 2, 9. All right, so you can see here how we can actually translate this system of equations over to matrix form. Now, what do we want to do when we're trying to find the solution through Gaussian elimination? We can create an augmented matrix and kind of change our given matrix into a row echelon or row echelon form. And so let me do that right here. And so let me change this matrix into an augmented matrix, and that's going to be very similar to what we have here, but it's going to be augmented, and hence the name. Let me bring that down over here like that, and let me take down this guy, and then I'm going to take the solution matrix and bring that onto this side. And so in doing so, I have created an augmented matrix. However, I still need to add one more thing, which is a dotted line as such. All right, so what are we doing? We have an augmented matrix over here. Augmented matrix over here. All right, so what we're going to do with the augmented matrix is actually going to manipulate it through row operations and bring it into triangular form or row echelon form. And so in doing so, we can actually make it very easy for us to solve the system of equations that we have above. And this is the same kind of thing that we're doing in the above, what we did in the previous example, except this time we're doing it through matrices. All right, so let's start off. Well, we can take this row 2 that we have over here, and by the way, this is going to be row 1. We have row 2 over here, and then this is going to be row 3. So we can take row 2, and we can take row 2 to be equal to its original minus 2 times row 1. And so what happens when we do that? Well, what happens is we're left with the same row 1. And let me make the augment over here. We're left with the same row 1. We're left with the same row 3. Row 3. But what happens to row 2? Well, 2 times 1 is going to be 2, and 2 minus 2 is going to be 0 over here. 2 times negative 3 is negative 6, and negative 8 minus negative 6 is going to be negative 2. And then 2 times 1 is going to be 2, and 8 minus 2 is 6. And then finally we have 2 times 4 is 8, and negative 2 minus 8 is going to be negative 10. All right, continuing on, we have a 0 over here. Let's see if we can bring down a 0 over here as well into this coefficient, so that now we have two equations essentially containing only y and z. So let's do that over here. Well, we can take, again, we can do R3 is equal to the original R3 minus negative 6 R1. And actually, if you want, I can actually just rewrite that as plus 6 R1. So doing that, let me scroll down just a little bit. Doing that, what we get is going to be the original row 1 and row 2. So the original, and let me write the augment over here, both the original row 1 and row 2. But however, for row 3, we have negative 6. 6 times 1 is going to be 6, and negative 6 plus 6 is 0. Then we have 6 times negative 3, which is going to be negative 18. And 3 plus negative 18, well, that's just negative 15. 6 times 1 is going to be 6, and negative 15 plus 6 is going to be negative 9. And then we have 6 times 4, which is 24. 24 plus 9 is 33. All right, we're on a roll here. We can continue on now to eliminating the y over here, right? And so we have this over here, and actually, in order to make this easier for us, what I can do is I can actually divide this whole row 2 by negative 2. So let's change that. We're going to have row 2 is essentially equal to negative 1/2 row 2. And so in doing so, we have the same row 1 and row 3. And I'm going to rewrite that over here. But row 2 is going to be 0, and then we also have 1, negative 3, and we have 5. All right, and that makes it much more easier for us to change the coefficient for the y in row 3, which is negative 15 right now. We want to change that to 0. What are we going to do there? Well, row 3 can be equivalent to row 3 minus 15, or sorry, plus 15 times row 2. All right, so what happens when we do that? Well, again, we have the same rows 1 and 2. The same rows 1 and 2. So let me keep that as is. Row 3, well, this 0 is going to remain constant because we have 15 times row 2, which is just going to be 0, and added that to row 3, well, again, it's just going to be 0. 15 times 1 is going to be 15. Add that to negative 15, that's going to be 0 over here. And then we also have 15 times negative 3, well, that's negative 45. And negative 9 plus negative 45, well, that's going to be negative 54. So we have negative 54 over here. And 15 times 5, a little complicated. Well, that's going to leave us with 75, and 75 plus 33, well, that's going to be 108. 108. All right, you can see the equation and the solution forming up. All right, and so what this translates over to is actually an equation, a system of equations that actually looks like this: x minus 3y plus z is equal to 4. Then we also have y minus 3z is equal to 5. And then we also have just negative 54z is equal to 108. Solving this out, this gives us z is equal to negative 2. We also have, plugging that negative 2 back into y equals negative 3z equals 5. We have y is equal to negative 1, because negative 2 times negative 3 is 6, and 5 minus 6 is negative 1. And then finally, we have x minus 3y plus z is equal to 4, plugging in the negative 1 and the negative 2 into y and z respectively. That's negative 3 times negative 1, which is 3. Minus 2 is 1. Bringing the 1 onto the other side, we are left with x equals 3. And that is the solution to the system of equation. Let's look at a real-world example of Gaussian elimination. Alright, so we're told that Manuel went to Italy during spring break, and the average daily hotel, food, and transportation costs for each of the cities are listed below. Write and solve a system of equations to determine how many days Manuel spent in each city, and they're also asking us to interpret our solution. Well, the first things we should probably do is create an augmented matrix for this table of values. So let's do that right now. Actually, the first thing I can do, before even doing the augmented matrix, is probably multiplying all of these values by 60, or dividing all of these first row values by 60. That actually makes it much easier for us, so let's do that. I'm not going to make it super huge, but I'll do it like this. So we have 60 divided by 60 is going to be 1. Then we have 2, 1, and then we're going to create the augment, and then we have 12 over here, and then we can keep the 40, the 90, the 30, this 490 total over here. So basically what we're trying to find is how much he's, how many days he's spending in each of the cities. And we know that our solution is going to reveal that because these are average daily costs. Alright, so the first things first, what we can do is we can actually, we can get rid of these, and this 40 and this 15 over here. And what we can do is we can actually say that row 2, we can say that row 2 is going to be equal to row 2 minus 40 times row 1, and row 3 is going to be equal to row 3 minus 15 times row 1. What does that leave us with? We're going to have 1, 0, 0 down the bottom, like that, or in that one column. We also have 12 over here. But then what is going to be the resulting, row 2 and row 3? Well, we know that, we know that 2 times 40 is going to be 80, and so 90 minus 80 is going to be 10. And then we also have 2 times 15, which is going to be 30, and 10 minus 30 is going to be negative 20. We also have 40 times 1, which is going to be 40, and then 30 minus 40 is negative 10. And then we also have 15 times 1, which is just 15, and 20 minus 15 is 5. 12 times 40 is 480, and so we have 490 minus 480, which is just 10 again. And 15 times 12 is going to be the same thing as 30 times 6, which is 180. And so 130 minus 150 or sorry, 180 is going to be 50, negative 50. All right, so what can we do from here now? Well, we can divide row 2 by 10 and row 3 by negative 5. So we can do that right now, actually. So row 2 is going to be equal to 1 over 10 times row 2. Row 3 is going to be equal to negative 1 over 5 times row 3. What does that leave us with? Again, we have the 1, 0, 0. We have 2, 1, and then 12 over here. Alright, so 10 divided by 10 is just going to be 1. We have negative 1 over here, and then we have 1 over here. Let me draw that correctly. Alright, then we're left with 4. We're also left with negative 1, and we have 10. Alright, so we have the setup over here where it's looking to be almost done now. All we have to do is get row 3 to be equal to row 3 minus 4 times row 2. You see what I'm doing here? I'm taking this, multiplying it by 4, subtracting it over here, and so this is going to result in 0 now. And so what does that leave us with? Well, we're going to be left with the same row 1 and row 2. So let me do that right now. Row 1 and row 2 are going to be the exact same thing. And then row 3 is going to be 0 over here. There's also going to be a 0 over here. But now it's going to be negative 1 times negative 4, which is 4. And so, or sorry, let's actually do 4 times negative 1, which is negative 4. And negative 1 minus negative 4 is going to be 3. And then we also have negative 4 times 1, which is just going to be negative 4. And 10 minus 4 is going to be 6. All right, so now we have this in reduced row echelon form, or sorry, just row echelon form. And so now we can actually solve, and we can convert this into a system of equation and solve for the number of days he spent in each of the cities. So let's do that right here. So we have x plus 2y. We also have y minus z, minus c is equal to 1. And then we also have 3z is equal to 6. All right, solving for z first, we're left with 2. Solving for y, we have y is equal to 3, I believe. And then 2 times, plugging the 2 into z and plugging the 3 into y. In the first equation, we are left with x plus 8 is equal to 12, and so x must be equal to 4. But actually, we're not done yet, because now we need to go back up, and we take a look at the cities. We have Paris, Lyon, and Marseille. Hopefully I'm pronouncing that correctly. So we have Paris, we have Lyon, and we have Marseille. Okay. So now we know that Manuel has spent 4 days in Paris, 3 days in Lyon, and 2 days in Marseille. And that is the solution to this problem. I'll be posting the whiteboard PDF onto the description of this video. Thank you so much for watching. If you have any questions, please feel free to leave them in the comments. Otherwise, thank you for watching, and yeah.